All right, so we're coming to the last of Kepler's 3 laws. Now, what he's done so far has been really radical, because he said that not only are the orbits of the planets not circular. Remember the old idea of uniform circular motion that Aristotle loved, that Copernicus held on to, that even our main man Galileo held on to, the idea of uniform circular motion of planets? Well, Kepler throws them both out. The first law removed the idea of circular orbits, right? The orbits are not circular, they're elliptical. All of a sudden, they're squashed circles. So that idea is thrown out. The second idea was of uniform motion, which means constant speed, right? That's what uniform circular motion means. Circular motion at a constant speed. Very dull. Very, very same today, same tomorrow, same next year, right? Well, Kepler throws them both out. No, Law 1 says, nope, not circular. Law 2 says, nope, not uniform, because remember the second law says when the planet gets close to the sun, it goes fast. When it goes far from the sun, it goes slow. So not only is it not moving in a circle, but its speed is constantly changing all the time. So the Earth's speed is changing right now. Right now it's getting slower. Okay. After July 1st, it'll start, May 3rd or 4th, it'll start speeding up again. But the speed is always changing. So not only is the motion of the planets not circular, it's not uniform. The third law is a little bit more mathematical. So Kepler's third law of planetary motion. I'm going to write it mathematically, then I'm going to unpack it. Okay? P squared equals A cubed. How's that for exciting? Huh? Boom. Well, we've got to unpack it, right? Because what's P? P is the period of the planet. Actually, it's what's called the orbital period of the planet. Whether it's Neptune or Jupiter or Mercury or Earth. The orbital period of the planet. All of that is how long it takes the planet to go around the sun once. For us, that's a sidereal year, right? Not the tropical year, the sidereal year. Okay, for the Earth, sidereal year is our period. It's a period of time. Okay, orbital period. How long? It's a time. It tells you how long it takes the planet to go around the sun. One full lap. That's the period, the orbital period. A lot of times we just call it the period. If we need to distinguish it from other periods, we'll call it the orbital period, but in general we'll just call P the period. Okay, the period of the planet. Can you see that? No, a big thing about collapsed on my head just now. Very dramatic, but luckily it didn't fall on me. So we're all good. A little weird, actually. Period is the amount of time it takes a planet to go around once. And the unit that we're going to use is Earth years, right? We can measure time in seconds, in hours, in days, in weeks, in fortnights, years, galactic years. You can measure time in any unit you want to. We're going to use Earth years. And by this, I mean sidereal years. But we don't need to make that distinction. Okay? So the period of the planet in Earth years. That's our P. A, we've already seen. A is the semi-major axis. We've already talked about that back when we talked about Kepler's first law. Again, it is the average distance between the planet and the sun. That's 93 million miles for the Earth. That's the average distance. Right now we're further than that. In January we'll be closer than that. But the average distance over a complete orbit is A, the semi-major axis. Okay. So this is a unit of distance Okay, and just like we can measure time with any time unit we want, seconds, years, fortnights, whatever, we can measure distance in whatever units we want. You know, feet, meters, miles, light years, furlongs, whatever, right? We can pick any unit of distance and measure it. We are going to use astronomical units. That is AUs. Now, 1 AU is not a mysterious unit. It's a big fancy name, astronomical unit, AU, but all that is 1 AU equals the Earth-Sun distance. Is this too far? No, it'll work. Okay. 1 AU is the Earth-Sun distance. So we could say that the Earth and the Sun are 93 million miles apart. We could say with complete equivalence that Earth and the Sun are 1 astronomical unit, 1 AU apart. In other words, 1 AU equals 93 million miles. Okay. 93, 1111000. That's an AU, 93 million miles. Okay. But when we put in the Earth-Sun distance here for A, we would put in the number 1 because we have to use, in this situation, when we use this formula, we have to use Earth years for the period, for the orbital period, and we have to use AUs, astronomical units, for the distance. Let's do an example. Suppose we know that for Saturn, that the semi-major axis of Saturn is 9.54 AUs. Now, all that tells us is that on average, Saturn is 9.54 times further from the Sun than we are. Our semi-major axis is 1 astronomical unit, 93 million miles, same thing. So this is 9.54 times further away from the Sun than the Earth is. If you wanted it in miles, you have to multiply 9.54 times 93 million to get the distance between the Sun and Saturn in miles. But when you use this formula, you have to use AUs. So we can now use this to calculate the period, right? The period squared is 9.54 cubed. Let's see what that number is. Okay. I didn't do it this way in my notes, so I'm going to do it real quick here. 9.54 cubed is 868.25. Okay. So the period is going to be the square root of 868.25. Right, if the period squared is 868.25, then the period itself is the square root of that. You take the square root of both sides of the equation, and when you do that, you find out that the period of Saturn is 29.4 years. Okay. That's how long it takes Saturn to make one whole loop of the Sun. So I first learned astronomy about 30 years ago. So Saturn has had time to make one orbit of the Sun since I first saw it in the sky. It's back more or less where it started when I first learned, okay, about astronomy. So that's how long it takes Saturn. And you can go the other way too, okay? I don't have room on the board to do that, but you can go the other way too. You can determine P given A as we did here, you can also determine A given P. Only difference there is you can't take the square root. In that case, you have to use the cube root to solve for A. All right, because A is going to be the cube root of whatever P squared is. So you have to use the cube root on your calculator to do that. Now what this basically tells us, the click and save of this law here tells us basically it relates the distance away, distance between the sun and the planet, and how fast that planet, how long it takes that planet to go around once. Okay. And basically tells you how fast the planet moves too. So planets that are further out from the sun go slower than the ones that are close in. Which you know probably. Mercury takes 88 days to go around the sun once, as we'll see. Whereas it takes Saturn 30 years to go around the sun once. So the closer a body is to the sun, the faster it moves. But this tells you exactly how, exactly what that relationship is. It relates the distance to the sun with the time it takes to complete one whole lap of the sun. That's Kepler's third law. All right. Now these laws that he came up with were tremendously successful. Kepler could have proven once, basically it was Kepler that convinced mathematicians and philosophers that the earth was moving and the sun was still. It was Kepler who really, I think, pushed the Copernican revolution sort of over the cliff and made it and completed it. Because these laws, all three of these laws, were not just, turned out in the end, they were not just true, they all worked for the planets that Kepler saw. But they all worked for Mercury, Venus, Mars, Jupiter, and Saturn. They worked perfectly. But they also worked for planets like Uranus and Neptune, which had never been discovered, had not been discovered at the time. So when these new planets were discovered, okay, they also orbited according to Kepler's laws. And the moons of Jupiter also orbited according to Kepler's laws. So in other words, Kepler based his laws on the motion really of Mars. Okay, historically, he was using Mars. But once he discovered these laws based on Mars alone, they turned out to be generally true. And this is the first time in history of astronomy, maybe of physics, where there were sort of universal physical laws. Kepler's laws were the first real true physical laws in history. Okay, and we still use them today. Phenomenal. So anyway, that's video 21 for you, and I'll see you next time for video 22, and we'll talk about Isaac Newton coming up.